Okay, so now we're going to look at the graphs, the properties of inverse functions in their graphs. So in example 4 from the previous lesson in the notes, we had two functions, a function and its inverse, and they were lines. So we were given this set of points or whatever. So if I graph the points for f of x, right, I graph them here, I get -3, -2, so it makes this, it's kind of like an orangish looking line or whatever it is. I'll use this color to trace it, right? We get this line here. That's my function f of x. I can say y equals f of x. Then if I switch the domain and the range for f inverse, I get this other table of values here. If I plot those, I'm getting this bluish line. And that line is going to be the graph of f inverse of x. And so the way that, what we notice about the graphs of the function of a function and its inverse is that the x and the y's were interchanged. So if I, again, the definition of an inverse is to switch the domain and the range, so it's kind of that simple. If I take my x and my y from my function and I switch them, I arrive at these guys as my new x and y, or my new domain and range, right? So that's all I'm doing. I'm switching each point. So I kind of call them like sister points. Like we can see that these two are like the sister points. The domain and range were switched. These two were switched. These two were switched, and so on, right? And those are just three that I've identified. An interesting one is the point right here where they intersect, right? That's the point 1, 1. If you switch it, that point's on both the inverse and the function. Another thing that's interesting that happens is as you start to graph inverses, a property of them is if I draw in this line, I'll make it dashed. They're always going to be reflexive about the identity line. And the equation of that line is y equals x. You can see that the two graphs, a graph and its inverse, are reflexive over the line y equals x. And that makes sense to me because if we're able to interchange x and y, that means that y is taking the role of x and x is taking the role of y. That means that those two things are interchangeable or they're equal to each other. So that's why it's reflexive over the line y equals x. Keep in mind geometrically what it means to be reflexive about a line is that the distance from any point to the line of reflection, that's the perpendicular line segment there, they're going to be equal to the other one. I didn't really draw it perpendicular, but I meant to. Those two distances to the line of reflection are going to be the same to those sister points. All right. So, in general, what I kind of want to say here is, if the point AB is on the graph of a function, then the point BA is on the graph of its inverse. All right, and that just really jives with our definition of what an inverse is. You switch the domain and range, or switch the x and the y. So here's an example. We're given a graph f of x. We want to graph its inverse. So I can identify some key points on here. I've got -2, 0. Whoops. That's a point on the graph. So if I graph, I'll do the inverse. I'm going to go in white. If I graph 0, -2, that would be right here. That would be the sister point. Actually, let me do the point and the sister point in the same color. I'll do them in pairs like that. So this will be at 0, -2. Then if I choose another point that I can easily identify, we've got 0, 2. On the inverse, it would correspond to 2, 0. Then we also have, let's do another pair. I can go 2, 4, this looks like, right? Is that 4? Yeah, 2, 4 is on the graph, so that means that 4, 2 would be on the sister graph. So wait, hold on, sorry, over 2, up 4, so yeah, over 4, and then up 2. So that would be on the sister graph. And then let's do one last one down here. Let's say this point here, this is what, -3, -2. So that means -2, -3 would be on the inverse. So then the inverse graph would look something like this, right? And again, we can see that it's reflexive about that line y equals x. So that's how we're going to plot. If we're given a graph, we're going to find some x and y, some coordinates, and switch the x and the y, and then plot the inverse. All right, so at this point, we should be well versed in determining if two functions are inverses to each other. Now we want to really turn our attention to, given one function, find the inverse, okay? And we already did that graphically here. But now we're going to look at how do we do it algebraically. So finding the inverse function. So if we think about how we just did it graphically, if the point AB, just recall what we said, right, lies on F, I'll just say on the graph of F, then the point BA, I should say, then the point lies on the inverse, or F prime, F prime, that's calculus, F inverse, all right? Also recall that there's symmetry about the line y equals x, so the y equals x symmetry tells us we can interchange the roles of x and y. So algebraically, that means we should do the same thing. So to find the inverse algebraically, so if we think about function notation, I'll say to find the inverse algebraically. So if we think of function notation, that means that we've said before that f of x kind of stands for the y value. So if I start with that statement, f of x equals y, that would imply if I do the inverse is going to be switch the domain and the range. So the domain is now y and the range is now x. All right, so for example, if I have a function and it's 3x minus 1, first what I want to do, well, actually, you know what, let's just do this example that we have here. I won't do a different example. Let's do the example that I chose. So we're going to do the same thing. So there's going to be steps. So the first step is we need to let f of x equal y. So we need to change our f of x to y. Right? We're just kind of doing this thing here. Right? We want to, that really represents y, so we're going to write it as y, because then step 2 is going to be to interchange the x and the y. So step 1 is, it's a simple step, but it's going to be to make that substitution there, replace f of x with y. So step 2 is then going to be to find the inverse. We're going to interchange or switch the x and the y. So now we have the inverse. I don't know if it's a function or not, but I do want to be clear. Sorry about that. I got to mute that. Actually, let's do this. Hold on a second. Okay, so I do want to be clear that this is the inverse already. As soon as you switch to x and y, you find the inverse. But is it a function? We don't know yet. Okay, it's not necessarily a function. So solving for y, if I'm able to solve it for y as a single function of x, as one equation, a single equation with just x in it, then I can say it's a function. So that's what we're going to work on now. Step 2 is to interchange the x and the y. Step 3 is to then solve for the y. See if we can do that. So if we square both sides, right, then we subtract 2. We end up getting, I'm going to put the y on the left side. We get x squared minus 2. We now have our inverse. We were able to solve it for y as a function of x, so therefore it is a function. I was able to solve it down to one equation. Okay, so then we're going to, since we were able to solve it for one equation, we can rewrite it in function notation. So this is no longer f, it's f inverse. Right, this is the function that's going to undo, this is the inverse of that function there. Now, the only thing you have to do, the last step, is to note any domain restrictions, or check domain restrictions. And keep in mind that the range of f is equal to the domain of f inverse and vice versa, right? So the domain of f inverse, when I look at this function on its own, that's not enough to check for domain restrictions. This is a parabola, so f inverse If I just look at it on its own, it looks like this. It's a parabola shifted down to. It looks like its domain is all reals, right, from negative infinity to infinity. But this function was obtained by finding the inverse of f. So I can't just say the domain is whatever the domain of this function is. I have to consider any, since it's going to be one-to-one, I have to consider what was the range on this original function. And the range of the original will become the domain of my inverse. So I need to kind of check domain restrictions by noting the domain and range of the original and also thinking about that as the domain and range of the inverse. So if I think of the original, I'm going to say that the domain of the function f, which is the square root function, is going to be any x values larger than or equal to -2, right? That's the domain of f. If you have a question about that, we can talk about in class how I came up with that. The range of f is going to be any y values that are bigger than or equal to 0. Again, I don't want to get into like how I came up with the domain and range. We can talk about that in class. But if you look at a graph of f, or you can just think about f, that's up to you how you figure that out. So the definition of an inverse is to just switch the domain and the range. So just looking purely at this, that means that the domain of f inverse is going to be the range of f. So whoops, now it's a domain, so now it's x's. I'm going to take this y is bigger than or equal to 0 and say x is bigger than or equal to 0. And the range of f inverse is going to be the domain. So now it's a y is bigger than or equal to -2. It will be the domain from f. All right, so we're going to say that our final kind of find the inverse is this is the inverse, but the domain is restricted, so we have to state that. So it's only for x bigger than or equal to 0. And how do we find that? There's kind of two ways. One way is you can kind of look, is there a domain restriction on this function? This is a polynomial, x squared minus 2, and there is not a domain restriction, so that's not enough. That's just one way to get started looking for the domain. What you really need to do is consider what was the range of the original function as well, and that's how you can come up with your domain restriction. So keep in mind, if I want to say that x squared minus 2 is the inverse of the square root of x plus 2, the square root of x plus 2 looks like this. The inverse function, if I didn't put any domain restrictions on it, would look like this. You can clearly see those two functions are not inverses of each other. The second one I drew, the inverse, has far more going on. It's got more points than the other one. There's not a one-to-one relationship. But if I restrict the domain to be just the x is bigger than or equal to 0, you can see then I get this reflexive about the line y equals x, and we're good to go. So that is a tricky part. You do have to consider what's the domain and range when finding the inverse, okay? Also, we want to be able to check, if we want to verify that we did find the correct inverse, we can do that. So I'm going to write that up here. Here's how we could check, because I'll ask you to do this in the practice. If f of x is the square root of x plus 2, and f inverse of x is x squared minus 2 for all x bigger than or equal to 0, we have to show their inverses by doing the composition of f inverse of x and show that it equals x, and we have to show it the other way. We have to show that these two functions, when we do the composition, they undo each other and we get left with just x. And we only have to show it on those domain restrictions. So it's based on whatever one is the inside function. So in other words, for this part, the inner function here is f inverse. So we just have to show that these undo each other on the domain of f inverse, which in this case, the domain of f inverse we said was x bigger than or equal to 0. And on the second one, we have to do it on the domain. We have to show that it works for the domain of f, because that's our inner function. It's going to only be as restrictive as whatever the domain of the inner function is, which happens to be x is, what was domain of x? Domain of f. X is larger than or equal to -2. So, as I do these checks, I'm going to do f of f inverse first. So I start with the outer function f. which is the square root of x plus 2. And I take out the x, and in its place, inside of it, I'm going to punch in whatever f inverse was, which was x squared minus 2. So then when I simplify, the minus 2 plus 2 cancel, I get the square root of x squared. And remember, for square rooting and squares, we have to consider positives and negatives, but not in this case because we're only dealing on the domain of f inverse, which is for x bigger than or equal to 0, which means 0 in all our positive numbers. So we know that this will simply come out to be x. It will not be, we don't have to consider negative x, so that's why it works. I just showed that the composition is indeed x. Okay, I don't consider the negative because my domain is restricted. If I considered the negatives, it wouldn't be the inverse anymore. That's why we have to restrict the domain. Okay, let's do it the other way now. If f inverse is my outer function, so that's like x squared minus 2, I remove the x and I plug in its place the inner function, which is f of x, which is going to be the square root of x plus 2. And that's going to be just over the domain of the inner function, which is all x values bigger than or equal to negative 2. So now if I start undoing this, I'm going to square and the square root undo each other. Then those undo each other, and I get simply just x. So when does this domain thing come into play? Really when you're dealing with like square roots and squaring and also absolute values. You know how we always say, well, there could be the positive or the negative. Based on the domain, it will tell you which one to choose. So that's where you really have to pay attention to this domain thing. Not really when you're doing just like dealing with other functions that don't have like a square root or any even powered root, okay? All right, let's move on here. So find the inverse of the function f of x equals absolute value of x if it exists. And I kind of say up here in the example that this does not have an inverse function, so it's not going to exist. But let's see how we kind of go through that. So one way to check if this function is one-to-one or has an inverse function, which kind of mean the same thing, is to graph it and see if it passes the horizontal line test. Okay, so it fails the horizontal line test because the horizontal line, I can draw one here that hits twice. So therefore, that's what these three dots mean. The function is not one-to-one. And another way is you can look at like the definition algebraically. If I replace f of x with y, then I interchange the x and the y. I remember this is the inverse, but it's not necessarily a function. As soon as I switch the x and the y, I now have the inverse relation. To be a function, I'd have to be able to solve for y and have only one equation for x. And that's not going to happen because the definition of absolute value means that I have two options. I could either have the positive or the negative version of y. So that's going to split into two equations with an or statement. And therefore, I cannot solve for y and only have one equation. That's how you would kind of show algebraically that it's not a one-to-one function. So this doesn't have one, so I don't have to find it. I'm okay with really just thinking about the graph and saying it fails the horizontal line test. I did just want to connect to this idea of an inverse being a function. I am, and you're on it because I just unpaused it. Everyone say hi to Mr. Cassidy. or Mr. Cassidy should say hi to everyone else. It's just
hello, everyone.
All right. So example 4.
Y equals mx plus b.
No, okay, we're doing rational functions now. So the function is a one-to-one. We don't have to check it. It's saying find its inverse. Okay, so step 1, replace f of x with y. Step 2, interchange the x and the y. Step 3, solve for the y. So in this case, I'm going to multiply both sides by the denominator. So I get x times y plus 3. Then I'm going to divide both sides by x. Then I'm going to subtract 3. Right? And so I'm having, I end up with 2 over x minus 3. And now for step 4, I'm going to replace and write it in function notation because I was able to solve for one single equation. Step 5, I have to note any domain restrictions. So if I think about the domain of this function right here, I can never divide by 0, right? So I know that x cannot be 0. So that's going to be our domain restriction. I should also check what's the range on the original function. So the function 2 times 1 over x plus 3, that's going to be shifted left 3. And it's going to look something like this. Again, that's knowledge of functions. I'm not going to get into that. It's going to look something like this, and you're going to note that the range is all y values except y cannot be 0. So we can see that that's how that turns in to the domain, because we switched the domain and the range for a function and its inverse. This one was nice because it just kind of appeared in the function like we kind of know that x can't be 0. That didn't really happen last time, but I did verify by thinking about the range of the original function. So note domain restriction. So here's our inverse. It said to find the inverse. So we did that. We could check. Remember, we can verify by showing that f of f inverse of x equals x, and f of f inverse of x equals x. So keep in mind what we're doing here is we're showing that f undoes f inverse and f inverse undoes f. So I'm not going to go through this. This one's pretty simple how it works out. If you have your two functions, f of x equals 2 over x plus 3, and f inverse equals 2 over x minus 3, you can do the composition both ways and show that you get down to x equals, or that it simplifies down to simply just x. Oops. So when we're talking about the sides, this will simplify down to x, and that will simplify down just to x. Okay, let's look at something called a piecewise function. The last example we're going to do today. So piecewise function, right, you have graphs in pieces, and there's already a domain restriction given to you there, so that's kind of nice, actually. I like this color. So determine whether the function is a one-to-one function. We're going to do that through graphing, for sure. So when x is less than 0, we have the function x squared. So that means at 0, if I plug in 0 to the top, I get 0 squared is 0. But I'm not including that because my domain is less than 0, so I'll leave an open circle there, though. Then if I plug in negative 1, I get 1. Negative 2, I get 4. So there is my graph, the first piece. That's for all x is less than 0. That's why I don't color in the circle at 0. I still have to find 0, plug 0 into the function, find out where to put the circle, the open circle, like how high do I put it? Do I put it at 0, 2, or 0, 0, or 0, negative 2? I have to plug it in to figure out where it goes, but I don't color it in because we're not including that point. We're including everything leading up to it. Okay, now, our piece number 2, for all x is bigger than or equal to 0. If I plug 0 into the bottom function, I get 0. So now I am coloring it in because of the second piece. 0, 0 is also on the second piece. Then when I go plug in 1 to the bottom, I get negative 1. I plug in 2, I get negative 2, and it looks like we have a line here. So if I look at this graph, does it pass the horizontal line test? It does. So therefore, it is a one-to-one function, which means its inverse is a function, so I'm going to go ahead and find it. So step 1, I'm going to kind of look at the two pieces. I've got y equals x squared and y equals x. I'm going to separate the two pieces. And this is for my domain of x is less than 0, and this is for my domain x bigger than or equal to 0. Remember that domain will come into play when you're dealing with like squareds into the force and absolute values. So that's why I really have to pay attention to it on number 1. Step 2 is to interchange the x and the y. So now I have x equals y squared. And here I have x equals y. Oh, this is supposed to be y equals negative x, sorry. So now x equals negative y when I interchange them. That's step 2. Step 3 is then solve for y. So here I go square root both sides, and I get y equals the square root of x. Now, it's the plus and the minus. Remember, when I square root, we have to consider both. That's what I was saying. But now, because of the domain restriction, I don't consider both. I'm only dealing with the negative values because x is less than 0. So I end up getting just that one. I don't have either the plus or the minus. I can eliminate the plus because of my domain restriction. Okay, here when I solve for y, I get y equals negative x. I just divide both sides by -1 or multiply by -1, however you want to look at it. And then I reuse my inverse notation and I write it as 1. I reinsert my inverse notation, function notation. So instead of y, I replace it with f inverse. And I'm going to write both parts together like we do for piecewise functions. So now it's going to be negative root x and then negative x. And then I have to put my domain restrictions on there. Now these are going to be actually the range. Remember, the domain of the inverse is the range of the original. So that's how I figure that out. Since we have the graph here, on this first piece, the range appears to be all values bigger than 0, and I don't include 0. Right? The range here was y is bigger than 0 because this was an open circle, remember, on the first piece. So if my range is y is bigger than 0, then that means that's going to become the domain on the inverse. Now I'm going to check the range on the second piece. It's going to start, it is including the 0, so it's going to be all y values less than or equal to 0. So when I switch that around to be the domain, it's going to be all, whoops, not bigger than, less than I just said, all x is less than or equal to 0. And that's how you would find the inverse function for a piecewise function.